Hi everybody, this is our lecture on section 4.1, functions of several variables. Recall the graph of a function of one variable, y equals f of x. So the function is f of x, and the equation y equals f of x represents the graph of that function. So the way one draws it is that you have your x-axis and then your y-axis, and you'll have a domain on the x-axis. All right, and then you have the curve for the function, and for every element x in the domain, the corresponding y-coordinate is f of x. All right, so this is the point x, f of x. All right, and that's how we define the graph of that single variable function. And a particular property of that graph satisfies the vertical line property. All right, that is, every vertical line intersects the graph in at most one point. Right? There's no stuff like this. I mean, like you have a circle, right? X squared plus y squared equals 1. Then here, vertical lines, they can intersect the graph twice. That's not a explicit function, y equals f of x, right? You can solve for y in a sense. It's this, right? But that's not a function. Given a value of x, I'm giving you two values for y. A function y equals f of x, for a value of x, you get one function of y. So this is often known as implicit. Y is implicitly a function of x. This is y is explicitly a function of x when you have the graph satisfying the vertical line property. All right. Now, and so here's a vertical line. And it's only hitting the graph in one spot. So now a function of two variables f, x, y. Okay, the domain of the function is the largest possible set of points x, y in the plane for which f of x, y is defined. So, for example, find the domain for f of xy equal to square root of x plus 5 y minus 1 square root. So in order for this to be defined, right, what is underneath the square root needs to be non-negative, bigger than or equal to 0, right? So we need that x plus 5 times y minus, well, x plus 5 is bigger than or equal to 0, and y minus 1 either. X plus 5 bigger than or equal to 0, and y minus 1 bigger than or equal to 0, or x plus 5 less than 0, and y minus 1 less than 0. So this means x is bigger than or equal to minus 5, and this means y is bigger than or equal to 1. This means x is less than negative 5, and this means y is less than 1. So in the xy plane, all right, here's the x-axis and the y-axis. Here is negative 5, x equal to negative 5. And this is y equals to 1 over here. Right, so bigger than or equal to negative 5 and bigger than or equal to 1, that's this region over here. Right? And then less than negative 5 and less than 1 is this region over here. By the way, we also count the lines themselves. Right? The lines are where that's fine. The lines are where x is equal to negative 5 and where y is equal to 1. And those areas count because that makes them equal to 0. And the square root of 0 is just 0. It's fine. It's algebraically defined. All right, so similar to this, find the domain for the function 1 over square root of x plus 5 y minus 1. All right, what about this? What's the difference between the domain for this two-variable function and the domain for the original one here? The only difference is that you can't have that either x plus 5 or y minus 1 equals 0, because you can't divide by 0. So let me recopy this. So the domain is the same, except we don't include those lines. All right, so domain is the same as before. But x is not equal to negative 5 and y is not equal to 1. So the way we sort of signify that would be to use dashed lines here, where these separating lines are hyphenated to indicate they're not counted as part of that set. They're just a boundary for that set. Should expand that, I think. Yeah, I'll make it look nicer a little bit. All right, how about this? Oh, well, let's talk about one other thing now. All right, the graph z equals fxy is the surface in the plane, in 3D space, consisting of all points x, y, and then z is f of xy. For xy in the domain of the function. So, for example, I'm sorry. So, in general, the idea is as follows. So, here is XYZ coordinate axes, and supposing that this was the domain here, in the XY plane, then the surface itself will be, this domain sort of lifted up or pushed down into a three-dimensional shape. So, right, so it's got some sort of contours, it's moving up and down. So this is z equals fx y. And if this is a point in the domain xy, 0 is a point in the domain right here, then when you go straight up or down to the surface, this is the point x, y, f, x, y for the z coordinate. And notice, right, this vertical line intersects the surface and it most one point, right? And that's again, a property from before. The graph z equals fxy also satisfies the vertical line property. Okay, so for example, find the domain. For the function equals square root 4 minus x squared minus y squared, and sketch the graph. Z equals square root 4 minus x squared minus y squared. Okay, well, here, so in order for this to be defined, we need that 4 minus x squared minus y squared is bigger than or equal to 0. Right, so 4 is bigger than or equal to x squared plus y squared. So this is the disk of radius 2. So the circle of radius 2 and all the points on the inside of it are the points satisfying x squared plus y squared less than or equal to 4. So this is the domain. Like that. And then the graph of the function, well, when you say z is equal to the square root 4 minus x squared minus y squared, that means z squared is 4 minus x squared minus y squared. That means x squared plus y squared plus z squared equals 4, which is the sphere of radius 2, but only the top half of it. Let me fix that. There we go. Only the top half of it, because z needs to be positive. Alright, so this is z equals 4 minus x squared minus y squared. It's the sphere of radius 2 centered at the origin. But it's just the top half, because z needs to be positive. We're missing the bottom half, right? If you tried to solve for z here, you'd have to have the plus or minus, and the minus square root thing being the southern hemisphere of that sphere. Okay. Oh, here's another, remember this example. All right, find the domain for f(x,y) equal to x squared plus y squared, and sketch the graph. Z equals x squared plus y squared. So here the domain is all xy, because it's a polynomial, and that's always defined. Right, and the sketch of the graph, well, for a fixed value of z, you have circles. So you have circles parallel to the xy plane, right? And then for x equal to 0, you have z equals y squared, which is the parabola. And you also have z equals x squared in the xz plane, and there is your surface. It is the paraboloid. So it's circles parallel to the xy plane, framed by these parabolas, called the paraboloid. Okay? Right. There's other ways to visualize a graph, and consider the following. So the second way is called level curves and the contour map. So level curves are a lot like what we were talking about with quadratic surfaces, just more specific. Given a fixed value for z, right, z equal to k, a constant. Okay, the equation k equal to fxy is a curve in the xy plane. Okay, using several different z values and graphing these all on the same xy plane. That's called a level curve. I should have mentioned that. All right, this is called a level curve. And then using several different z values and simultaneously graphing them all on the same xy plane yields what's called the contour map. The contour map for z equals fxy. So rather than trying to draw the surface in a three-dimensional fashion, we draw in a two-dimensional fashion with several level curves. So for example, so this one is similar to that saddle surface, but it's much easier to draw now. So make a contour map for z equals square root x squared plus y squared. So now, certainly z has to be bigger than or equal to 0. So if we say z is equal to 0, then we have, not plus, x minus. We have 0 is equal to x squared minus y squared, so 0 is x squared minus y squared. Now what does that look like? So 0 is equal to x minus y times x plus y. Well, x minus y equal to 0, that's just the line y equals x, right? And the line y equals negative x is that one. Right, so this is the contour for z equal to 0. Now, if z is equal to 1, then they have 1 is equal to x squared minus y squared. So 1 is equal to x squared minus y squared. And that is the hyperbola intersecting the x-axis at 1 and negative 1. So it's this hyperbola. So that's the contour, or the level curve, for z equal to 1. And then for z equal to 2, right, you have 2 is equal to square root x squared minus y squared. So 1 is equal to x squared over 4 minus y squared over 4. So that is the hyperbola intersecting the x-axis with these asymptotes at 2 and minus 2. So, looking like that. And that's the contour or the level curve for z equal to 2. And the, contour for z equal to 3 is going to be similar. And so on and so forth like that. All right, so there's the contour map for the function. Now, that can be a lot easier to draw than trying to draw the three-dimensional surface. So this one is similar to that saddle surface, although it's a little bit simpler. But it looks like this. So you have that x, the line y equals x, and y equals negative x, in the xy plane, like that. And then you've got these lines kind of sloping. It didn't really work out too well. Guess we're going to have to flatten it out. There we go. And then you've got these lines sloping upward. And actually, in this drawing, this is the x-axis, this is the y-axis, and that's the z-axis. And then you've got these hyperbolas hanging here. So and then over here, same kind of thing. All right, so that's the kind of picture that you're going to get there. Connecting to this here. That didn't work out too well. I'll just leave it as it is. Okay. That's square root. All right. How about functions of three variables? So that's functions of two variables, domains, and ways of viewing them. Surface z equals f of xy, and the contour map for z equals f of xy. We can also do some things with three variable functions. Oh, I forgot to mention. Not only is the contour map perhaps easier to draw, but it has some very special properties that we'll get to when we talk about the gradient vector. And by the way, you've probably all seen contour maps at some point or another, probably in your high school classroom. Right, when you see these topographical or elevation maps, so maps with elevation curves. Yeah, so should be some nice pictures here of that. Here's one. Oh, that's YouTube. Or yeah, here's a picture explaining it. Right. So when you see a map that looks like this in your high school classroom, or in your college classroom, perhaps, what does that mean? Like this curve right here is where the elevation of the land is 10,000 meters. This is where it's 20,000 meters, 30,000 meters, 40,000 meters, 50,000 meters. So this picture kind of, gives a convenient image for this picture here. Okay, and we'll get to a nice application of the calculus, the three-dimensional calculus, to these level curves when we start talking about the gradient. Okay, so that's a nice intuitive picture for what this contour map could be. All right, functions of three variables. Given a function of three variables, f, x, y, z, okay, the domain is a solid region, possibly infinite, in 3D space. All right, so you'll have, in 3D space, you'll have this solid region, and that is the domain of your function, the largest set upon which that function is defined. All right, so x, y, z, and that's the domain. But now the range is on a number line for w. So this is the range, and this function takes a point x, y, z, so say over here, x, y, z in the domain, and takes it over here to this point w equals f, x, y, z. Now, we can no longer visually think of the graph anymore, unless somehow you're good about thinking about four-dimensional things. The graph of the function lives in four dimensions, and there are techniques that you can use to think about four-dimensional things, and I'll mention that in a moment. That's not something we really want to get into in this course. So one can no longer easily visualize the function because it lives in four dimensions. So different ways of thinking about the function. One may think of f of x, y, z as a function that measures the density in unit mass per unit volume at x, y, z. right? So at this point x, y, z, this solid domain has some kind of density in units of mass per units of volume. Or as the temperature at point x, y, z. So, for example, like you've got this object, this domain object in three-dimensional space, and you've got some heat source right there, right? It's radiating out heat. And then you have the function f measuring temperature. And the temperature over here at these points is going to be hotter than over here, right? Up here, it's a little cooler than here. Down here, it's a little cooler than right there. So on and so forth. The temperature will decrease as you go as you go further away from that heat source. Okay, so thinking of F as temperature or density of a point in the domain is a typical way of thinking about these three variable functions. Okay. The level surfaces we call the surface k equal to f, x, y, z, the level surface rather than level curve at k. And that's a way you can think in 4 dimensions. You think of k or the z coordinate as time. So as time moves forward, what do the level surfaces do? How do the level surfaces change? Okay, that's not an easy way to think about things, but it's one thing you might do. But I mean, as far as level surfaces go, one can draw one level surface or maybe a couple level surfaces to get an idea of what that function is doing. So one might draw one or more level surfaces in x, y, z space. So, for example, if you had f of x, y, z equal to 1 over x squared plus y squared plus z squared, right, then the domain is all x, y, z except x, y, all x, y, z not equal to, x, y, z not equal to 0, 0, 0. So as long as you're not 0, 0, 0, the bottom there is the x squared plus y squared plus z squared is not going to be equal to 0, and you can do the division. So if you take, it's always positive. So taking z equal to k, which is strictly positive, maybe we'll say 1 over d squared, strictly positive, the level curve, or k squared, for f, x, y, the level curve, 1 over k squared equal to 1 over x squared plus y squared plus z squared is the sphere of radius k. Right, so that's the level surface. The sphere of radius k. Oops, I only drew half of it, didn't I? There we go. So this is w equal to 1 over k squared, and it's got radius k. So as k is increasing, the level surfaces become smaller and smaller spheres. Right, so for small values of k, this is a large number, and you get larger spheres. Right, so for values of k like 1 over 10 million or something like that, you get a large sphere. For values of k equal to 10 million, you get a really tiny sphere. Okay? So it's often, if you can draw more than one level surface, you might. I mean, it's kind of hard to draw one sphere inside of another, without some special drawing techniques. But that's one way to look at a function of 3 variables. Okay, so that's the end of the lecture on this section.